In this video, we will learn how to find out the maximum or minimum of a multivariate function and how to use the Hession Matrix in checking the second order condition for minimum or maximum. The question is, determine whether the function v is equal to minus x cube plus 3xz plus 2y minus y square minus 3z square has a minimum or maximum obtain the extreme values. Okay, so let me rewrite it. So can I write v? It is a function of three variables, that is x, y and z, which is equal to minus x cube plus 3xz plus 2y minus y square minus 3z square. Okay, given this multivariate function, to find out whether the function is minimum or maximum, we use the first order condition. For first order condition, what we check? We take the partial derivatives with respect to x, y and z and set them equal to 0. So first order condition for minimum or maximum is, that is, we take the first partials, that is first derivatives with respect to x first. So f subscript x means the partial derivative of this function with respect to x. Okay, so derivative of x cube will be 3x square, and here we have x, so here we will get derivative of x is 1, so we are left with 3z, and no x is involved in other terms, so their derivative will be 0, and we set this equal to 0. Likewise, we take f subscript y means the partial derivative of this function with respect to y. Okay, so derivative, since no y is involved in the first two terms, their derivative will be 0. Derivative of y in the third term is 1, so we are left with 2. Then we have derivative of y square is 2y, so we will get minus 2y, and we set it equal to 0. Likewise, we take f of z. Okay, and differentiating partially with respect to z, derivative of z in the second term is 1, so we are left with 3x, and we have z in the last term, derivative of z square is 2z, so 2 into 3 is minus 6 z, and we set it equal to 0. Having said that, to check whether the function is minimum or maximum, we use the first order condition. First order condition, how do we check? We take the partials of the given function with respect to x, y and z and set them equal to 0 simultaneously, and then solve them. Okay, so let us see how to solve these questions. Okay, how to solve these equations rather here. So we have minus 3x from first equation. We have, if I transpose it here, so we will get 3z is equal to 3x square, dividing both sides by 3, so we will get z is equal to x square, which gives us x square is equal to z. Okay, this comes from this equation. Okay, so in the second equation, we have, if I solve this, so we will get 2y is equal to 2, dividing both sides by 2, we will get y is equal to 1. So far we got one critical value for y, which is 1. Now in the last equation, we can write 3x, transpose it here, it is equal to 6z, dividing both sides by 3, this gets cancelled, so here we get x is equal to 3 1s are 3 2s are 2z. Okay, what we have now? We have x square is equal to z, y is equal to 1, and x is equal to 2z. Now if I plug x is equal to 2z in this equation, so what will I get? In place of x, I write 2z in this equation, so we get 2z square is equal to z, which is equal to 4z square is equal to z, dividing both sides by z, so z gets cancelled, we are left with 1, here 1z gets cancelled, so we get 4z is equal to 1, which gives us the value of z is equal to 1 upon 4. Okay, then what will be x? Since x is equal to 2 times z, so x will be equal to 2 times 1 upon 4, which is equal to 1 upon 2. Okay, so what we got? We got the critical values here, that is, we got x is equal to 1 upon 2, y is equal to 1, which we got in the first place, and z is equal to, let me write it in this fashion. So the critical points are x star, y star, z star. They came out to be, so x is 1 upon 2, y is 1, and z is equal to 1 upon 4. Okay, now let me rub this out. So we got the critical values for x, y and z here. This was about the first order condition. So these pointers tell us the point where the first order condition is met, where the function is either minimum or maximum, okay. But to see which among these, okay, whether the points are minimum or maximum, for that we need to check the second order condition, okay. So we need to check second order condition. So for that, what will we do? We construct a Hessian matrix, okay. So what is Hessian matrix? Hessian matrix is a matrix of second order, what we call second order partial derivatives of the given function with second order direct partials on the principal diagonal element, Let me explain it here. So what will be the Hessian here? So it will be a matrix composed of the second order partial derivatives with second order direct partials on the principal diagonal element. Let me write it here. So we have f subscript xx, f of xy, f of xz. Likewise we have f of yx, f of yy and f of yz. Then we have f of zx, f of zy and f of zz. So what is the Hessian matrix? It is a matrix composed of second order partial derivatives with second order direct partials. That is second derivative with respect to x, second derivative with respect to y. These fxx, fyy and fzz, these are called the second order direct partials, and all other f of xy or xz, these are called the second order cross partials, which are on the either side of the principal diagonal element. So we need to check out, rather find out these derivatives here one by one. So first things first, so we need to find out f of xx. What does this mean? F of xx means the partial derivative of this first derivative function with respect to x. So f of x is this, again differentiating with respect to x, so we get the derivative of x square is 2x, so 2 into 3 is minus 6x, okay. Then we need to find out f of xy. Let me write it here. So let me write it here, f of xy. That means we differentiate it with respect to y, this function. Since no y is involved, its derivative will be z, sorry 0. No y is involved here. Then we have f of xz. That means partially differentiating with respect to z. Since z is here, so derivative of z is 1, so we are left with 3. Then we find out f of yy, f of yy. That means derivative of this function with respect to y. Derivative of y is 1, so we are left with negative 2. Then we need to find out f of yx. Since f of xy is equal to 0, f of yx will be also equal to 0. Now why I am saying this? If f of xy is equal to 0, then f of yx will be also equal to 0. It is by Young's theorem. Okay, if we have a function, let us say f of xy, let us say it is equal to x square y. Okay, so let us take the partial with respect to x. So we will get here 2xy. Let us take f of xy. You can see derivative of this with respect to y. So derivative of y is 1. So we are left with 2x. Now let us take derivative of y with respect to y. So derivative of y is 1. So we are left with the derivative of this function with respect to y will be 1. So we are left with x square. Now f of yx, the derivative of this function with respect to x will give us 2x. Here you can see f of yx is 2x and f of xy is 2x. Okay. Then we need to find out f of yz. Okay. f of yz. Since no z is involved in this and we have to differentiate this with respect to z, so its derivative is 0. Let's find out f of zz. F of z is this. F of zz will be derivative again with respect to z, so we will get negative 6. Then we have f of z y with respect to y, so here we will get 0. Let us take f of zx. Okay, since x z is 3, f of x z is equal to 3, then zx will be again 3. And here we can see z with respect to x, since x is here, so we get 3. Okay, now let us plug these values here in the Hession matrix. So what will we get? So h will be equal to, so we have f of xx, which is negative 6x. Then we have 0 here in place of xy. Then we have 3. F of yx is 0. F of yy is negative 2 here. Then we have f of Hamza Okuna, f of yz. Let us find out where is yz. It's again 0. Then we have f of zx, which is zx is 3. Then we have zy, which is 0. Then we have zz, which is negative 6. Okay, now what we do, this is our Hession matrix. Now we take the determinant of the principal diagonal, the minors along the principal diagonal. That is, we find out h1 will be this very minor, that is minus 6x, and we evaluated it the critical point. Since no y and z is here, we have only x. Let us give the value of x. So we have minus 6 times 1 upon 2, so we will get negative 3. Okay, let's find out the second principal minor, that is h2. So what is second principal minor? This is our first principal minor. Hamza ma karke. This is first principal minor. Now second principal minor will be this 2 by 2 matrix. So let's take its determinant. So we have minus 6x. So we have minus 6 times the value of x is 1 upon 2 times this negative 2. From this we subtract these two elements. So 0 into 0 is 0. We will not write it here. So what we get here? So we get negative times negative is positive. So we get here positive 6. Here you can see h1 is less than 0. h2 is greater than 0. Now let's find out the third second order principal minor. So that will be this whole matrix. So h3, the determinant of h3 will be, so we write, how do we take, if we have 3 by 3 matrix, how do we take matrix? Let me explain it here. So we write the first element first. We have negative 6 times the value of x, we know the critical value, which is 1 upon 2. Okay, we write the first element, then mentally delete the row and the column in which it appears and multiply this 6x with the determinant of the remaining elements. If I delete this row and this column, we are left with this 2 by 2 matrix. Now what will be its determinant? Let us find out. So we have, how do we find out determinant? We multiply these two elements first. So negative 2 into negative 6 is positive 12. Then we write, we subtract and multiply these two elements. So 0 into 0 is 0. Okay. Then we write minus and write the second element, which is 0, and delete mentally the row and the column in which this second element appears, and take determinant of the remaining element. So the remaining elements are 0, 3, 0, negative 6. So 0 into 6, it will be obviously 0, minus 3 into 0 is 0. Then we write plus and write third element, and first to mentally delete the row and the column in which it appears and take the determinant of the remaining elements. So remaining elements are here. 0 into 0 is 0, then we have minus, then we have 3 into negative 2, which is negative 6. Okay, so let us see what we will get here. So 2 1s are 2 3s are 6, so we get 3 into 12, which is negative 36. So 0 times this, it will be 0. Then plus negative into negative is positive, so we get 6 into 3, which is 18. So here you can see we got 18, which is positive. Okay, so what we got actually, we got H1 is negative, H2 is positive, H3 is negative. Okay, if the principal minors of Hession matrix alternate their sign from negative to positive, we get a sufficient condition for I guess this is the sufficient condition for, so if they are all positive, then we get minimum. So this satisfies this condition for maximum. Okay, I am getting always confused. Okay, if the Hessian determinants alternate their sign from negative to positive, we get a sufficient condition for maximum. If H1, if all are positive, if H2, which is not case here, if all are positive, then we get a sufficient condition for minimum. Okay, so in this case, x, y, z, where x is equal to 1 upon 2, 1 and 1 upon 4, they satisfy the second order condition for maximum. Okay, why? Because the Hessian, that is the second order principal minors of Hessian matrix alternate their signs. Okay, now we have to find out the corresponding maximum value. How do we find out the maximum value? Simply plug the values, these values x, y and z, in the original equation. So we have v of 1 upon 2, 1 and 1 upon 4. Plug these values in this equation. So we have negative 1 upon 2 cube plus 3x. So let's write it is x, it is y, it is z. So then we have 3xz. So 3 into 1 upon 2 into 1 upon 4. Okay, then we have 2y. 2 times y is 1. Then we have negative y square, means 1 square. Then we have negative 3 times z is 1 upon 4, go 1 upon 4 square. So let's find out what we'll get. So here we will get in the first term, we will get 2 to 4 to 8, negative 1 upon 8. Then we have 3 upon 2 4 to 8 in the second term. Then we have 2 minus 1 is 1. So it can be okay. So then we have 4 4 to 16. So here we get rather negative 3 upon 16. Okay, so here we get 3 into negative 1. So we get 2 upon 8 plus 1 minus 3 upon 16. Okay, so 8 can become 16. So let us multiply it with by 2. So here we can write 16 upon 16, 16 upon 16 in place of 1. So we get 2 to the 4, 4 plus 16, 4 plus 16 minus 3 upon 16. So we get 17 upon 16. That means maximum value will be 17 upon 16. I hope I make myself clear and you find out this video helpful. Thank you.